So I'm really glad to be here, first of all. So I'm from Huawei. I was invited to do a few lectures here about the topic which I would like to choose, and I decided to do the lectures about object-oriented programming. This is something I work with for many years, and I have something to share with you today. I created this Telegram group for everybody who will be in these lectures. So you can join now. We will share the news in this group. We will share the information about future lectures. I will post the homework there. Everything will be in this Telegram group. So if you join right now, you will be able to know what's going on. We're going to talk for 90 minutes today. It's going to be 40 minutes, 10 minutes break, and then 40 minutes again. It will be about object-oriented programming. By the way, if you have any questions during this lecture, you can ask them right now. It's going to be interactive. So the idea is to make the lectures interactive. So it's not like the whole lecture and then some time for questions. You can ask me questions while we're talking. Then when I finish, when the 90 minutes is over, then I just go home and you go home and that's over. So that's why all the questions are expected during the lecture. And you can ask them right in the Telegram group. So I have my phone here, so I will check the group and I will see your questions. So we will talk about object-oriented programming. Who of you actually write code? How many of you are actually programmers? So raise your hands, people who write code. Okay, that's great. That's what I was expecting. And how many of you actually write object-oriented code? Like Java, Swift, C#, C++. All right. And what is the main language for you? What kind of language do you use? C++, Java, what else? C#, Python, anybody? All right. Okay, so I give you, first of all, I give you some quotes about object-oriented programming. This is the first one. Object-oriented programs are offered as alternatives to correct ones. This is a very famous quote from this guy. It was said long time ago. It's, who knows this person? You should, if you are, yeah, you definitely know. He's the author of a lot of scientific work, and he said that object-oriented programming is something which, we don't like. And actually it's true, and that's why I'm gonna talk to you. We're gonna have 8 lectures about object-oriented programming, and I will tell you that actually he's right in so many cases. The second quote is this one. I invented the term object-oriented, and I can tell you that I didn't have C++ in mind. So that's the quote from Alan Kay. Alan Kay was actually the inventor of object-oriented programming. So he coined the term. He suggested to say object-oriented programming. And as you know, as we all know, he is not happy about what we have right now on the market and what we know as object-oriented programming. It's definitely not what C++ gives us, and definitely not what Java gives us. The next one is object-oriented programming offers a sustainable way to write spaghetti code. So I give you quotes of people who are very famous on the market and who criticize object-oriented programming. This is Paul Graham. Who knows Paul Graham? Who ever heard about it? It's quite famous person among Lisp developers, and he's famous in Silicon Valley. He's the co-founder of Y Combinator. It's one of the biggest, or probably the biggest incubator for startups. And he also claimed some time ago that object-oriented programming is something that we should not use. The next one is object-oriented seems to bring at least as many problems to the table as it solves. So it solves some problem, but at the same time it causes even more problems. So object-oriented programming is what people don't like. This is Jeff Atwood. Who knows this guy? He's the co-founder of Stack Overflow. Who knows Stack Overflow? You definitely know. So he was one of 2 people who founded Stack Overflow, and he also doesn't like object-oriented programming, and he has his reasons for that. And the last one is C++ is a horrible language. C++ leads to really bad design choices and this blah blah blah, some idiotic object model crap. This one comes from Linus Torvalds. So you probably know this guy, right? So he is the creator of Linux operating system. He also doesn't like C++. He also doesn't like the C++ programming. And So that's it. So that was the introduction to give you an idea that we have a problem. That was my point. We definitely have a problem on the market now. We have object-oriented programming, and there are so many people who are not happy about it. They are not happy about the quality of software they write using object-oriented languages. And this is the structure of the talk today. So first of all, I will explain you who I am. I'll give you some introduction about myself. Who knows me a little bit, at least. So who knows me from something? Okay, just one person. So I'll introduce myself so you know who I am. Then I will tell you the story of how I met my first algorithm. That was a long time ago. I will explain you a story of the algorithm. This lecture is called Algorithms. Then I will give you the object-oriented alternative, as far as I understand it. So I'll show you how we can do it better. Then we're going to discuss why Java doesn't do it the way I think we should do it. And then I'll give you the plan for future lectures. So that's the plan for today. That's how it's going to be structured. So let's start with who I am. I started writing code 32 years ago. I was 12 at that time, and this is the first computer. This is my first computer. That's the computer I met at this time. It was quite slow. Even the picture has a broken keyboard. So that's really, really long time ago. The computer had like really small amount of memory, and it had the language which was called BASIC. Who ever wrote anything in BASIC? A few people. We're going to use BASIC today too. We'll have a few languages today. I got my master's in computer science with a focus on databases 10 years after I met my first computer. 10 years later, I met GitHub. The GitHub showed up on the market, and I started to use GitHub, and I started to become an open source contributor and developer. Who of you are actually do something on GitHub? Who contributes something to GitHub? Okay, that's amazing. And 10 years later, not 10, but 8 years later, I wrote a book called Elegant Objects. I actually have one of the copies of this book with me, and I'm gonna give it as a gift to one of you today. It's the book I wrote about object-oriented programming, which basically explains everything I'm going to share with you over the next 8 lectures we're going to have here. And then I wrote that was the book I published 4 years ago about object-oriented programming. And this is my activity on GitHub. I am the author. I mostly write in Java. This is my primary language, Java and a little bit of Ruby. And I am the author of these 2 open source products, takes.org and cactus.org. You can check, you can find them on the internet. Those are Java libraries which are written the way I think Java code should be written. So my understanding of object-oriented programming is a little bit or a lot different from what many people think object-oriented programming is. And I will show you what I have in mind, and maybe, I hope, some of you will share my passion for proper object-oriented programming. And now I am the director of Systems Programming Lab. I just joined Huawei about 5 months ago. And that's how I got here. So this event is sponsored by Huawei. So I work in Huawei. I have a small lab of about 40 people there. We have programmers there, researchers, a few interns, people who are at the same time work in Huawei, and they keep studying in their universities, in their high schools. So we are looking for interns, actually. So the main objective of these lectures is to encourage you to come to me later, to talk to me, and to join Huawei as an intern. So being an intern, you work inside our lab, you get some money, you come and go, you spend like 20 hours a week, 30 hours a week, 10 hours a week, as much as you want. At the same time, you stay a student, you remain a student, and you work with us, and we pay you, and you solve some interesting tasks which we have in the lab. So I am with Huawei for the last 5 months. The lectures will be shared on YouTube channel. So everything we record today, everything will be published probably in a few days after each lecture. So you may attend the lecture, you may watch the lecture later. Everything will be published. You may subscribe to the channel. And that's enough for the introduction. I told you everything I wanted to tell about myself, about the basics, and now let's get to object-oriented programming. Any questions up to now? I think you know everything you need to know about me. Prepare your questions. The best question will get the book. And now let's start with a simple piece of software, which I wrote 30 years ago. That was my first piece of software, actually. This is a game in the language called BASIC, a game which makes you guess, which makes the computer make up some number, some random number, and then the user has to guess the number. And the computer says, is it too big or too small? Is it too big or too small? And then by giving the answers to the computer, you have to find the right number. This is language called GW Basic. The language was created by Microsoft a long time ago, and I wrote this piece of software a long time ago. Let's see how it works. The first line, do you see my mouse? No, you don't see it. So the first, all the numbers, all the lines in GW Basic are numbered with the numbers. So every line in the code has to have a number. Number 10, 20, you can put any number there. You can name them 1, 2, 3, 4, but by convention in BASIC, all lines are numbered with 10, 20, 30, etc., etc. So on the first line, number 10, we make up a random number. R&D is a function. R&D ones means the number is random in the random number from 0 to 1. Then you multiply it by 100, and then n will be what? N? From 0 to 100, from 0 to 99, I think, because the actual number will be from 0 to, it's not going to be 1 ever, it's going to be from 0 to 99. The next line is that we set t equals to t plus 1. So what's going to be t now? What's your guess? In BASIC. What's going to be, what t will be equal to after the line 20? It says t equals to t plus 1. It's going to be 1, correct. Because t, all the variables in BASIC, they're at 0 by default. So t equals t plus 1. So t is going to be 1. T is the try. So the position of the try. So how many tries the user did. And then we say if t more than 5, then we go to line number 120. 120, we print you lost, sorry, it was, and then we print the actual number which the computer made up. Here we used goto. So BASIC is the language with a lot of goto statements. Who of you use goto now in your software? So probably nobody, because you know that goto was the statement was considered as a bad idea in general, and now all the modern languages, even though they have goto statement, even Java has goto statement, but people don't use it because we all agreed many years ago that goto is something we shouldn't use. But in BASIC there was no other option. We had to use goto. So here that's why in the line 30, if t is more than 5, so we made too many attempts already, so we just jump to line 120 and we print you're lost, thanks for playing with me. If we don't jump, then the line 40 we print guess a number, and then we ask the user, and line 50 we say input x. Input x means ask the user for something, and whatever the user says, put it into variable x. That's how BASIC works. And then we compare. If x less than what we have in our memory, then we print too small. If x is more than n, then we print too big. If x equals to n, then okay, that's it. You made it, you guessed the right number, and then we jump to the line 100, and at line 100 we say bingo, you got it, you got the number, and then we do go to 130, we jump even below, thanks for playing with me. Otherwise, on the line 90, we go to 20 and start again. Increment the t and start again and again and again. This is the very typical way of writing software in BASIC. There's no object-oriented programming here. Just simple variables, statements, go-to statements, comparison, and so on. And who didn't manage to understand the algorithm? Everybody got it. I was asked when I was a kid, when they were teaching me programming, they told me that flowcharts is the way you design your software. First of all, is the way you think about your software. You have to design a flowchart. A flowchart is you put the rectangles there, you put the bigger rectangles, smaller rectangles, and arrows, and that's exactly the code you just saw. This is the basic code in the form of algorithm. That's how it should look if you design the basic software. The same here. So first of all, you start, and then you stop. It's usually always the algorithm starts with the start on the top and then stop at the bottom. And then you do forking, you do conditions, comparisons, yes, no, exactly the same we had in the basic code. So actually programmers, that's what I was told, that's how they trained me when I was a kid, that when you start designing your software, you put this flowchart first. You think like a flowchart. You put everything in the rectangles, you connect the rectangles, and that's how you make your software. That's how you design it. And then, after you design the flowchart, then you get the language like BASIC or Pascal, or there will many other languages, and then you convert your thinking into the software. The algorithm was coming first. The algorithm was always in front of the programmer. That was the idea. The programmer had to think in form of an algorithm, in form of instructions given to computer. There's a computer in front of me and I give instructions to the computer. Let me jump back to one slide. So those are instructions I give to computer, like do this, do that, go to, that's exactly specific instructions I give to the computer. So the algorithm was the king. The algorithm is always in front of us. It was the king. It was important to understand the algorithm. And then other languages I started to grow, and I started to meet new languages, other languages. For example, I met this one. Who knows what kind of language is this?
Pascal.
Pascal, exactly. That was Pascal. That's the language which does exactly the same. Exactly the same logic, exactly the same algorithm, but written in a different language. It does very similar things, exactly the same things. First, it uses sysutils. I tested it, so it works. First, we need to define variables, so we need to define them first, not like in BASIC. You can just use them, and that's it. In Pascal, you need to define them, n, t, whatever, then the type. So there were types introduced. And then you randomize, you put all the statements are not numbered anymore, so you don't need to number all the lines. You just put a semicolon at the end of the line. And but the logic is exactly the same. N equals to random, you randomize it, then t equals to 0, and then you do the while end, while true, do begin, and then you do incrementation, and then you break your while when the user is lost, and you break, otherwise you print, right? You do exactly the same, but now we don't have the go-to statements. That was actually an achievement, so that was good. So the Pascal language and other languages, which I will show you now, they actually resolved the problem with these go-to statements, and now we don't have go-to statements anymore. We have a a better way to explain the algorithm, but still. The algorithm is in front of us. We still give instructions to the computer. We still tell the computer what to do. We, as a programmer, we know exactly how the computer works, and we see the whole algorithm through the whole software. So we look at this software and we think in form of a flowchart. Our thinking is still procedural. That's the key word I'm going to use today, procedural. So we think like a procedure, we give instructions. Sometimes we say implicit, imperative instructions. So we tell the computer exactly what to do, and we expect the computer to react immediately and then let us make the next step. So we think like a flowchart. A, B, C, if not, left, right, A, B, C. We flow from the top to the bottom. We flow, our thinking goes from the top to the bottom. I will show you now what's the opposite way, what's the different way. But now, yes? Yeah, the question is what's wrong with the go-to? Let's get back a little bit. So maybe somebody can answer, but I'll try. So what was wrong with the go-to? That's, we have so many go-to statements here, and that was okay with the basic programming language, but it was considered by many people a long time ago, probably like 25 years ago or so, maybe 30 years ago, that go-to statements, they make code way less readable then structures like while, do, if, then, etc., etc. So when we need to, when we use go to, it's difficult for us to understand the logic of the algorithm. It's difficult for us to understand where we are standing while we're thinking like the algorithm. For example, if you look at this, this flow chart, then here there is no go to. So this flow chart doesn't have go to. It has structures which are at different levels of not of an abstraction, but on different levels of indentation. So something, for example, you lost stays in its own separate area. And we know that if we go into this territory of lost, then we are in some other place. We're not in the main flow. So we have actually basically 3 places which are standing aside from the main flow. You lost, too small, too big. There's 3 places which are different, and they're subroutines or sub-functions or sub-blocks of code. With the go-to, you cannot say here, looking at the code, which one is sub-block, which one is a subroutine, which one is standing aside from the main flow. Everything is the main flow for you. It's just main flow without any indentation from the left. When the Pascal language, we have indentation. So now we know that what's indented right, it's something from a sub-level. And while looking at the algorithm, we don't need to think about the whole set of instructions. We just need to think about our level of indentation. So when I look at it, for example, while true, and then I go down and I see if, then begin, and I can ignore what stays on inside this block, and then keep thinking lower. So for me now, thanks to these structures like if, then, and without go to, I have different levels of indentation, which creates some subroutines or sub-blocks of code or sub-functions inside the code. So that was an achievement, actually. So go-to it was inevitable from the assembly language. The assembly language didn't have anything like subroutines or something. So it was always necessary to use jump, not even go-to, but jump. So basic was also using go-to, which was considered a bad practice by many programmers long time ago. So go-to is bad. That's the definite bottom line. So Pascal, we get rid of go-to, even though Pascal has go-to statement. Like I'm saying, C, C++, Pascal, Basic, Java, all languages, they still have go-to statements. It's still possible to use it, but it's considered as a bad practice by so many engineers that if you find somebody writing go-to statement in the code, you can definitely say that there is something really wrong with the program. So Pascal, we have, the code looks better, thanks to the indentation. Indentation was an achievement, actually. However, we still look at the algorithm. We see the full flow. We think from top till bottom. We think like computers. We start here, we go down level by level, step by step, maybe going a little bit, left and then returning right, but we still flow like a flow chart. We flow from top, we flow till the bottom. And it's bad. That's my point, which I will prove to you later. So this is very imperative way of thinking. Imperative means that you imperatively, directly telling to the computer what to do. The next language I learned was, what's the language? C. C, exactly. That was the language C, which I learned when I was in, probably your age. And it was actually a next step after Pascal because it was more powerful, more interesting, and so on and so on. And the code looked like this, not so far away from Pascal. Again, still the same algorithm, the same indentation. Instructions are a little bit different, functions, whatever, but the main idea is the same. It's the same flow chart. It's the same game, the same guessing game. But just written in a different syntax. Then I learned another language, which is Java. That's right. That was the language I learned when Java showed up. So I was writing in Java 1.0. That was the first version of Java, which was very primitive, not as powerful as it is now, but very basic. It was not far away from C++. It took many features from C++. It took many ideas from C++. It was Java. So Java was labeled like object-oriented language, as well as C++ actually. C++ was also labeled as an object-oriented language, and Java was object-oriented language, so there were objects, but still this code doesn't use any objects, doesn't use any classes. It's still the same implementation of the same algorithm, the same algorithm for guessing, for playing the game, and it works. You can compile it. I will share you the slides in the Telegram group. You'll be able to play with it. So that was Java. And then after about 10 years of working with Java, I found out that something is wrong, that I actually don't like this code. I don't like the way of writing this code. So the question is, how else? So how can we write the same code, the same algorithm, but differently, completely differently? And now I'll show you how, in an object-oriented way. So I will show you now step by step. There will be like 6 steps how we design this software, and then you will see how this software looks in the end. And then we'll discuss. Step number 1. We need computer to make up the number, to create a number, a random number. So I create a class. I create a class for this number, and I call this class secret. The secret class encapsulates the number which we make up. The secret class has 2 constructors. Can you explain me what happens in the first constructor?
The class gets the random number from 0 to 99.
And then? Like what? It calls another constructor, right? So the first constructor calls the second constructor. You see this, right? Yeah. So in the first constructor, which has no arguments, we create this random number and call another constructor, the second one, which actually encapsulates the number. Okay? So these 2 constructors are called, the first one is called primary, the second one is called primary constructor, which stays on the bottom. It's called primary constructor because it actually encapsulates the number. And the first constructor is called secondary because it doesn't encapsulate anything, it just creates something and calls another constructor. And then we have a method which returns the number. So in order to create a random number, we do it like this: int n new secret dot number, right? So if you call the code like this, then you will, in the n will be a random number. This is the piece of code, the object, which now is a number created by the computer. This is the number computer makes up and remembers. The next step, we need to ask the user, what is the number you are telling me? What's the number you want to give us? Another class. I call this class guess. Guess is actually what the user is doing, guessing. So the second class is guess. How does it work? I say the method number, and in the method number I print guess a number, and then I use scanner with the input stream, and then it returns me the next integer. So this is basically how in Java you ask the user to enter something. So the user gives me the integer, 1, 2, 3, enter, and boom, my method number will return what the user says. So if I call this code below, then what's going to happen? The console will say, guess the number, the user will type in something, enter, boom, the number goes in as an X. Make sense? So now we have 2 pieces of code, 2 objects. The first object is the object which is the number created by the computer. The second object is the number which the user enters. 2 objects. Now the next step. We want to know the difference between 2 numbers. And I can create the object number 3, which is called diff, because of the difference. So object number diff, the object by the name diff, encapsulates 2 objects. The first one is secret, another one is guess. Secret is secret, guess is guess. And then we have a method number, which returns the difference between these 2 numbers. So what will happen when the code below will be executed? Let's think. We have the first object secret, we have the second object guess. I can jump back a little bit. This is the object secret. Remember?
The difference between the secret and the guess.
This is the object called guess. So what will happen when this code will be executed?
Diff is the difference between...
Diff is the difference, but what's gonna what will be in the diff and what will happen on the screen?
The constructor of secret will print the text to the...
Secret, what will secret do? Look at the code. Do we have this, the line, the light? No? Yeah. So you can think for a minute. Okay, yeah. So let's try. So we have, this one is encapsulated, this one is encapsulated. I encapsulate secret and I encapsulate guess. And then I call number. When I call number, I jump in here and then I call this guess dot number minus this secret dot number. So this one will say, hey user, please enter the number, right?
Yeah.
We will enter the number and the number will be returned. It's 1, 2, 3. And then the secret will say, try to make up the number. And the computer will build the number here and will say, my number is 10. So 1, 2, 3 minus 10 will return 1, 1, 3 or something. So when I run this, the console will say, give me the number. You enter it, it compares with what we have for the computer and returns the difference. So as you can see, there is no algorithm here. You don't see the algorithm anymore because the algorithm is in 3 places now. This is the place which compares numbers, and then we have 2 objects somewhere here and here, which is secret and guess, and they do their jobs, and together we will get the difference.
Isn't it that every time we call diff, the secret number generates again?
Correctly, yes. Every time we call diff, the secret will be renamed. The secret will make up another number. So secret will remember another number. That's correct. That's true. So we will have again and again returning. I mean, the computer will make up a different number every time. That's true. We will deal with this in a minute. Let's try to put these pieces together and imagine this code. This is the real code in Java. So it's a static method. We say printf, so the difference is, and then our code. So if you call this, if you run this software now, the software will say on the console, what is your number? My number is 72. Boom, the difference is 15. That's what's going to happen when you run this code. It's like part of our game. It's still not the full game, but it's part of it. It's like a small element of the whole game. Let's make the next step. Let's make another class, which is verbose diff, which encapsulates our diff inside, and it makes the code a little bit more complex. Look at this. First of all, it calls the number from the encapsulated diff. It also says, give me the number, what's inside. And then it doesn't print like in the previous slide here. It doesn't print the difference because we don't want to show the actual difference to the user. We want to say, if it's less than 0, we say it's too small. If it's more than 0, we say it's too big. And if it's equal, we say bingo. And in all 3 cases, we return the difference. So this class is also a diff. It behaves like a diff. It also returns the difference. But when it returns the difference, it says, is it too big, is it too small, or you hit the number. So it makes our code additional, it adds additional functionality to the diff. It extends our algorithm, it extends our logic by decorating the diff. And if you put it together now, in the whole code, then if you run this code in Java, this one, you run it, and what will happen? In the console it will say, guess the number, 17. It will say too big, and the software will finish. So that's the next step towards the whole game. Next step is we want this to happen a number of times. So we want to make multiple attempts. We don't want to quit after the first attempt. So how do we do this? How we don't quit? We make another class, attempt, which encapsulates the verbose diff and the maximum amount of attempts we're going to give to the user. So again, we have the method called matches. Okay, with the method called matches, which inside has a cycle. That's the attempt, that's the t, which we had before in all our code. And we say while t is less than maximum and the difference is not 0, then increment t. And then return t is less than maximum attempt or more. This cycle will make exactly what? Guess the number. 1, 2, 3. Too big. Try again. 1, 1. Too small. Try again. 7, 7. Boom. You lost. Not lost, but you will return in the end. You will return when there are too many attempts. So we make our algorithm a little bit more complex. Now we have attempts. We do the cycles. So this object represents the game which makes a number of attempts. How many attempts? As many as we encapsulate here. So we can use this code. Yeah, and then the final step. The final step, we call this class farewell. We say bye-bye. This is the final class. The final class encapsulates the attempt, encapsulates the secret. The secret which we have. Because we want to say what was the secret in the end. And it has the method say. What it does, it says if the number of attempts doesn't match, then we say you lost, and otherwise we say thanks for playing with me. If you lost, we say it was, and then we print the actual number. We put all the pieces together like this. This is our software. This is our game in an object-oriented style. This is the main entry point for Java. Then we make up the secret. We say secret, new secret, in order to get rid of the problem. So we only once make the instance of the class secret, and the actual random will happen inside the constructor. And then we go new farewell, new attempts, new verbose diff, new diff, secret here, guess here, how many attempts, we pass the secret here, and we say. And this will play the game. And if Java would make it possible, then actually the only problem here is that I don't like this line. We say secret here, and then we put it here, and then we put it here. So actually we need this line just because we need to reuse the secret here and here. Would be even better if Java would allow us to use it like this. It's not Java code now, it's just my code. So I say new secret as secret. So like call it secret later, and then we call it here. So this is the perfect object-oriented code. The beauty of it is that first of all it's declarative. Here is the code which was before. So this is declarative object-oriented code which doesn't show us the algorithm. You cannot understand from here how this game works. You only see what this game is. You see that the game consists of the farewell, bye-bye message, it's some attempts, and then it's very verbose, and then it calculates the difference, and then the difference is made up between the secret made up by the computer and the actual number entered by the user. What's happening inside, you don't see it and you don't want to see it. You look at the software, you look at your software as an object, as a composition of objects. Your software composes a number of objects, each object does its own job. And all together, they play the algorithm. So this is the wrong way of writing software. This is what all the people I mentioned before call that the object-oriented is spaghetti code. This definitely is spaghetti code. This is the code which nobody gonna like. This is object-oriented programming, which is different, which actually everybody will like and understand. And I will explain you during the next 7 lectures. This one was the introductory lecture, and then we're going to have seven other lectures where I will explain you how to design your Java or Python or C# code so that it looks more like this and less like that. So this code is actually, like I said, this code is very imperative and procedural. It's still the same old procedure like it was long time ago in the languages like BASIC and Pascal. This one is more declarative. So we don't say what to do, we declare the intent. We say we intend to have a secret, we intend to guess, we intend to have a difference between them, and then we intend to have a number of attempts, and actually we intend to say bye-bye in the end. We put these intents together, we encapsulate one into another, and then boom, we have a code. It's easier to write because it's imperative. We just give the instructions to the computer and it's so fast, boom, 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 the code is there. This one takes more time to think about these classes. So which class to encapsulate which, how to put them together. It takes some time, it takes some work. That's true, that's definitely the case. I took this example from my book. So this is the code in my book here. And it took me to write this maybe, I don't know, half an hour. This one, I think 2 days or so. So I was thinking a lot how to design it. And you will do the same. But when this code is here, it's way easier to maintain the code, to test it, to write unit tests, to debug, to do a lot of things. So in object-oriented programming, that's a good comment. We spend more time to design, to think about the right allocation of classes. But then coding is much easier. Extending the system is much easier. So let me give you more visual examples of what's going on. This is our code. And take a look at the visual presentation of it. So we have the class guess. We have the class secret. Secret and guess. They are encapsulated inside diff. The diff is encapsulated inside verbose diff. And then the number 5 is encapsulated together with the verbose diff inside attempt. And then this whole thing is encapsulated in the farewell together with the secret. So this is the visual object composition of our software, which is very close to functional composition. So if you write in functional languages, you will know what is functional composition. And you can Google it, you will see that functional composition is very close to this. Here is object composition. The ideas are very similar to each other. They're close to each other. Functional composition and object composition. You can find 2 articles in Wikipedia. One is called object composition, one is called functional composition. So this is the architecture, this is the design of our code. And now let's put these pieces like this. So now we've just, put them separately. And to assemble the code, we just put pieces in the places where they belong. We took secret and guess. Where do they go? Here. And then we take diff. Where the diff goes? In here. And then we take verbose diff. Where does it go? Here. And 5 we put here. And then we take attempt and put it in the large piece here. And here we put the secret. So the object-oriented software is supposed to be assembled like small puzzles in the large picture. Just put these pieces together and they should fit easily. And then the whole software just starts to work. That's the idea of declarative programming. I'm not trying to give you now the exact instructions. We will spend more time to discuss exactly all these things during the next 7 lectures we're going to have. This one is an introductory lecture to show you that algorithms are bad. Thinking in algorithms is thinking like we were doing that in the past. We need to think about design. We need to think of blocks which we put together in order to make our software. If you think about how your computer will execute your will execute your instructions, then you are just an algorithm writer. You're not a designer. You will not be able to make a large object-oriented software, and your software will always be spaghetti code. So designing algorithms in an imperative way is the past. The future must look like this. There's no instructions, there are no go-to statements, there are no flow charts. There are only blocks of functionality, blocks of entities. Those things are entities which you assemble together, and then boom, all of a sudden your code starts working. And of course this approach is good for unit testing as well, because you have very standalone elements and you can unit test it easily. And if you know what it is, mocking. Who knows what mocking is? Mocking is not the technology, is the methods of testing the code. So take a look. For example, we want to test how the secret works. So we want to know that the class actually does what it has to do. So how would it do it? We write unit test. Who knows what a unit test is? Almost not everybody, but half of you. So unit test is another code which we write in order to test our code. I cannot give you an example right now, I didn't prepare it, but it's easy. So you take the class which you designed, and then you create another class which will call this class automatically and check, does it return what it has to return? It's easy to do when your class is small, but when the class is larger like this one, you want to test only this part, but you need these pieces to be there in order to work, in order for diff to work. So how do you fill these elements if you want to test this code? The first option is actually to get these two and put into these small holes. Just put them there and test this whole thing together. But this is not always possible. Sometimes it's not possible, sometimes we don't want to put everything in place in order to test just this class. Then we use mocking, so-called. So we put here some fake objects, not real objects, but fake, or mock, as they call them. So we put fake objects in these places, and then we run the test to see how the diff works. When the design, that's my point, I'm not going to explain in details, but my point is that when design looks like this, testing is way more easy. It's much easier than comparing to the algorithm you may have. A long algorithm when you need debugging, when you need to go line by line with the debugger in order to understand where the mistake is. Here, you test elements individually. Each piece you test individually. So the question is, why object-oriented programming world is different? So why everybody writes code, why writes spaghetti code, and not so many people write this object-oriented software? Everybody writes algorithms still. And why people keep saying that object-oriented programming is spaghetti, is a bad way to write code, and Linus Torvalds hates C++. Why it's happening? What's going on? I don't know exactly. I don't have an exact number, but I have my theory. I think it's a combination of two factors. The first one is the flexibility we give to programmers. We give a lot of tools and a lot of instruments in each programming language for us programmers to do whatever they want. Who read this book by the creator of C++? You said you write in C++. So you have to know this book. It's a fundamental book about C++. It's actually a huge book. It's a really big book. So if you want to know C++, you need to read this book. This book explains the language which was the most popular object-oriented language. There was Smalltalk before, there were some other languages, but C++ was the mainstream, widely supported by Microsoft, and it was used in the Windows and designing Windows operating system. So C++ is a huge language. And if you look at C++ right now, if you look at the keywords which we have in C++, this is the list of all keywords in the modern C++ language. We have 95 keywords. 95 keywords in a language which programmers are supposed to remember, to understand how they work, and to know what it is. So the language is complex, that's my point. The language is very flexible. You can do many things. You can do a lot of things using many instruments. And this flexibility gives you an ability to do too many wrong things using these tools and instruments. So I think that languages, modern languages, starting from Java is also growing every day, and every new language, every new version of Java introduces some new feature for the language, something new. So the language becomes more and more flexible, powerful and flexible. And I think flexibility is bad. I think that flexibility given to programmers actually encourages programmers, provokes programmers to do something wrong, to design their software in the wrong way. And if we have an ability to do it imperatively, if we have an ability to do it the way, as an algorithm, then of course we're going to do it. If we can use, for example, in C++, we have the goto. So we have goto. It's a keyword, it's a statement in C++. If we have it, we can use it. Some programmers sometimes will say, yeah, why not? We have goto, I can do goto, and I do it, and the software works. Boom. That's the flexibility I'm talking about. So I think flexibility gives programmers an opportunity, especially bad programmers, junior programmers, bad programmers. It's not the same, but close. So junior programmers, they will look at this and say, wow, that's amazing. Let me try this one. And they try it, and it works. Oh, cool. And they let me try this one. And they keep trying, and they think, that if it exists in the language, this is the way the software has to be written. So flexibility actually pushes us the wrong way, give us the ability to design it the wrong way. And that's problem number one. And the problem number two is the bazaar we have on the market. Who ever heard about this famous book and the article essay in the beginning? The Bazaar versus the Cathedral. It was written a long time ago, actually. I was probably a student at that time, maybe even younger. So a long time ago was written the essay which, the bottom line of this book, the main message is that there are two approaches to design software. The first approach is like people design cathedrals, like we put architects together, they take a piece of paper, they draw everything on the paper, they discuss how the software or the building has to be done, they put all the measurements there, they put numbers, they understand, they think about it, and then they agree, and then they start building. So that's like a more thought forward. So you think first and then you build. That's how I understand it. The alternative to this is more like a bazaar where people just offer whatever they have, and the one who speaks louder wins in the end. So it's like basically a chaos, the total chaos, which is right now the software market. So there are, I know how many hundreds of programming languages on the market. Anybody can create a new language. And then the language which was for some reason more interesting to everybody else just wins. Like Ruby, for example, the language which was created by just one programmer a long time ago, and boom, this is the language which is top 10 language in the world. Not only languages, design patterns, ideas, everything. So there is no one central place where people would think how we programmers need to design software. No central place. There's no committee who is sitting together every month and saying, okay, now we think that the right way for all of us to design software is this. No, it just happens randomly. We give programmers languages, we give them instruments, and then they start creating whatever they want. So we give them flexibility and we don't control them. And of course, they start making whatever they want. And of course, not the best software, not the best ideas win, unfortunately. Unfortunately, wins whatever works. That's the message of software development of the last 40 years. Whatever works. If it works, it's good. If I can design it the wrong way, but it works, it's good. Unfortunately. I actually don't, I feel sad about this situation. I see this situation, I understand it as I'm being a programmer as well. And I see that in most cases, programmers who I work with, they're always people who think like this. If it works, whatever. Why do you want me to design it properly? Why do you want me to redesign it? It works. The computer understands me. The computer understands me, and that's why it's good. And this is the mentality, this is the way of thinking, which I think ruins the market a lot. And maybe I'll say something obvious, but I think that the market 40 years ago and the market now, which you will be working in, is two different markets. 40 years ago, when I was a kid, computers were very expensive. Computers were super expensive. They were like, each computer cost like I don't know, like a few cars. And they were very slow. They were very expensive and at the same time very small, very slow. It was absolutely impossible to just extend the amount of operating memory like twice or make it faster or it was like there were a lot of hardware limitations. And we programmers had to deal with these limitations, and we programmers were extremely cheap. So our salaries were low, we were not expensive at all, and computers were expensive. So that was like, the balance was like this. Computers were kings. Computers were dominating the market. They were telling us what to do. We were like inexpensive resources. Now the situation is quite the opposite. Computers are cheap and programmers are way more expensive. So now, if long time ago we were writing software for computers, it was important for us to write something which computers will understand. If I write the way computer understands me, I'm a good programmer. Today, I have to write for programmers. If I write for computer and other programmers around me don't understand me, then I'm a bad programmer. Because my code is not maintainable, my code is not readable, and if I go away from the project, the code will have to be rewritten, will have to be changed, will have to be thrown away, and somebody else will have to write it from scratch. And that's expensive. Long time ago, it was not expensive. Okay, your code doesn't work, we don't understand how it works. We throw it away, we get another programmer, he's cheap, she's cheap, just put these people on board and they will design it from scratch. It's okay, it's no problem. The problem is to get not to lose the computer. Now, it's completely opposite situation. If you write the code for computers, you're not in the market. You have to write for people. You have to write for your friends, for people who will come after you to this code and work with this code. So this model, the bazaar, is less effective now. So now it's not actually in our favor. So we don't want to be like this anymore. We don't want to write whatever works. So this motto, like it was a long time ago, whatever works, it doesn't apply anymore, it doesn't work anymore. We need to think differently. We need to think like, will this code be easily to read and maintain in a year, in 2 years, when other people will join the project? And I think when you will be professional programmers, like in 10 years, I think the situation will be even worse. Computers will cost nothing. Like, for example, now the storage is getting more and cheaper and cheaper and cheaper, cloud storage. In 10 years, probably it will be just free. You will, like right now, YouTube is free. If you publish your video there, it's free. You pay nothing for it. I publish all of my videos. I put no ads, no promotion there. It's like free. So I post my data in the cloud for free. I think that in 10 years, any data will be posted for free. And maybe the computation power will be free. Meaning that you will be able to get the computer from the cloud for free and give the computer instructions. The computer will just work for you. It will be free, probably. Most likely it's going to happen. But you, programmers, will cost 2 times more than you cost now. So if you compare me right now with me in 10 years, it will be 2 different people getting a different amount of money for each hour of work. I think in 10 years I will cost 2 times more, and you too. And computers will be cheap. So this is the tendency. It means that we have to write for people. Not whatever works, not algorithms, not like if computer understands me, I'm a good programmer. No. You have to write what other people understand. So that's like philosophical side point. So what we have on the market right now? We have, like, for example, 3 basic languages. So what happened? Again, like explain you the situation. What happened is that some people sometimes ask me what I think about Java, what I think about Ruby, what is the best language? Which one is the best language for object-oriented programming? I think that most languages are, except C++, of course, most languages are good. And yeah, it's a joke about C++, but that's close, because C++ is extremely complex language. It's very complex for no reason. That's my point, that C++ is the language which has a lot of complexity for no reason. You don't need that complexity. This could be way less complex and more simple. So if you look at these 3 languages, then what you deal with right now, it's not the languages, it's the frameworks which cover these languages. It's not the Java now, it's Spring framework. It's not Ruby anymore, it's Rails framework, Ruby on Rails. It's not C++, it's Windows. So well, I'm not sure about the Windows, but it's something like this. So languages are now covered by frameworks designed by somebody else. So the language by itself was not bad, like Ruby, for example. Ruby is a great example. Ruby is a very interesting, very powerful, really object-oriented language. But if you look at the frameworks which are created on top of Ruby, like Ruby on Rails, for example, then you have a completely different story. You have some garbage, if you ask me. So this is completely not object-oriented, something which is really difficult to read and not possible to use. That's my understanding. Java, the same in Java. If you look at Java, it's a good language. If you look at Spring, it's a completely different story. So now we unfortunately have to deal with Spring, Rails, Windows, and all that stuff. And let me show you what we're going to talk about. Let me show you what I think is wrong, for example, in Java. So these things are mistakes in Java, I think. So all of these elements exist in Java, and we will discuss over the next 7 lectures why they are mistakes. Why I think, for example, private methods should not be used. Why I think private methods is a mistake. Why I think that inheritance in general is a mistake. Is something which should not exist in Java or any other object-oriented programming language. Why I think that null, for example, is something which came from C and should not exist in proper object-oriented language, in Java, for example. Why I think that static is the wrong keyword in Java and any other language. So there should be no static methods, no static variables, nothing static, no static blocks, of course. So all these elements, which constitute actually 80% of Java language, 80% of Java language is actually these keywords, is actually these features. So if you look at Java and remove this stuff, then you will get a perfect language. Then you will get a language which is properly object-oriented. But how many frameworks will work with you then? Nothing, nobody, because all frameworks are based on these features. And Java keeps adding more features, which I think should not exist there. And C++ keeps adding more features, which I think they should not exist there. So now the whole industry is moving towards more flexibility, more bazaar, and less clear and less obvious design. So here's the plan. We have 5 more minutes. So here's the plan for next lectures. This one was called algorithms, and it was today, 11th of March. The next one we're going to discuss static. So I will explain you why static is wrong and how to get rid of static and why we should not use static. Then we're going to discuss getters. Who knows what is getters? Many people. So we're going to discuss why you shouldn't know what it is. Then we're going to talk about setters. You probably know what setters are. That's even worse than getters. So we're going to discuss why you shouldn't use setters. Then ER. Who knows this problem in object-oriented programming? So that's the very common, that's a very famous idea, is that any class that has a name which ends with ER is a bad class. Controller, router, parser, printer, analyzer, anything, dispatcher, it's all wrong. If you design something which is called like this, you're doing it wrong. Not my idea, but I will explain why I agree with this idea. The next one is null. We're going to talk about null, why it's a big mistake and what to do instead. This one about reflection. Who knows what reflection is? One person. First of all, I'm going to teach you what it is, and then I'll tell you why you shouldn't use it. Well, you should know how it works, of course, but we're going to discuss why it's a bad mistake. And, of course, we're going to discuss inheritance. So inheritance is a terrible mistake in object-oriented programming, in my opinion, not only my opinion. We're going to discuss why it's a bad idea. So that's the plan. And this is your homework. I'm asking you to take a look at this GitHub repository. I will send you the link in the Telegram chat as well. So you take a look at this repository. It's a very simple Java project with only one Java class. It's a game, another game. Today we had one game. Here's another game written in Java. It compiles, it works, it's a hangman. So you know the hangman. So I give you the word, and you have to guess the letters, and you don't guess the letter right, then I'm going to hang you on I'm going to draw the hangman. It works in Java. I'm asking you to design it in the object-oriented way. Right there in the GitHub. So design it and send me the pull request. Whoever designs it right, whoever designs it better, the next time, in the next week, next Wednesday, we're gonna discuss, and I'll give some gift for the person who does it better. So using the slides we have today, I'm gonna share them right after the lecture. I'm gonna share them in Telegram, so you can use the slides, think about it, and redesign the Java code from this repository the right way, and send me the pull request. Make sense? Mm-hmm. Probably the end for today. If you have any questions, we have 5 more minutes. You can ask them, and I'm going to give you the book. The book which summarizes almost everything I said today. Yeah, go ahead.
Can you use C++ in the homework?
Can you use C++ in the homework? Yes, I think you can. I think you can try it, but make sure it compiles and it works. So I can check that it actually works and it actually plays. I can play it on my computer. So you send me the pull request. I'm going to check it out on my computer. I have Mac, so I compile it. And if it works, then yes. You can use any other language, actually. Python, C++, whatever. Yeah.
Разделение спагетти кода на кучу объектов сильно влияет на производительность?
Yeah, the question is about performance. So if we take the spaghetti code, this algorithm, long algorithm description, all algorithm code, and then we split it into objects, and what about performance? Definitely, the answer is yes, it's going to affect performance. Of course, it's going to be slower, most probably. But, like I said, Now the key problem in most cases, not in all cases, but in most cases, is not about performance. Computers are fast, computers are cheap. The problem is the maintainability of the code, understandability, readability. So how clean is the code? So definitely performance will suffer in most cases, but in most cases it's not going to matter. It's going to be okay. If your software works not in 5 milliseconds but in 10 milliseconds, but your code is easy to understand for all other programmers, in most cases you're going to win. Sometimes, in very, very corner cases, your customer will say, you know what, it's too slow. We need not 10 milliseconds, we need 5 milliseconds. In this case, you can do something in some specific places in your code and say, okay, here, instead of 2 objects, I'm going to use spaghetti code. But it's going to be a very conscious decision, not just everywhere spaghetti code. Yeah.
What can you say about Python? How can you compare it with Java and C++ in all those aspects?
What I think about Python? Yeah, I think that Python was, not I think, but I know, as far as I know, Python was a scripting, the language for scripts, and was not for object-oriented programming, just like PHP. And then they made it object-oriented, as far as I know. So they just got, okay, we have PHP, we have so many people who use PHP, how about we introduce objects? How we introduce inheritance? How we introduce method overflow? Something like this. And the same they did for Python. So Python was not designed as an object-oriented language. That's why I think Ruby is the best object-oriented language. It was originally designed as an object-oriented language. Like everything is an object, all the methods are you can override any method. So Python, I think it's kind of surrogate, like a hybrid language. It's not object-oriented, it was originally a language for simple scripts, like Perl. But then they said, okay, how about object-oriented, because everybody likes objects, so let's do objects. So if you learn a new language, I would suggest Ruby, honestly, but stay away from Ruby on Rails. So if you learn Ruby, learn Ruby. Don't learn all the frameworks, especially Ruby on Rails, which gonna completely cloud your mind and will completely give you the wrong idea of what is object-oriented programming. Yeah?
Is using patterns a good idea? For example, we could use a singleton when we were talking about secret in our example.
I think that most patterns, some patterns are good, but singleton is definitely a wrong pattern. And I'll explain next time, next session. We'll talk about singleton when we talk about static. But some patterns are good. For example, decorator is a very good pattern, but there are many other patterns. Most patterns introduced by people, researchers, they're bad, unfortunately, because they were introducing them mostly in order to, to justify the mistakes they made. So like they look at the people who make the same mistakes everywhere, they write spaghetti code and they say, now it's not spaghetti code, it's the pattern. And now this one is not spaghetti code, it's a singleton. But in general, they're just mistakes made by many people at the same time. So I would suggest to stay away from most of the patterns. We can discuss which one. I can give you names specifically, which I think which pattern is good, which one is bad. Maybe next time I'll give you the list. Yeah.
Will we consider open technologies like Scrum or Keys? And what do you think about functional programming?
About functional programming, like I said, I think it's very close to object-oriented programming. They're very close, but object-oriented programming, in my opinion, is more powerful because objects have state. Functions, they don't have state. It's more difficult for me, at least. I was programming in Clojure. I was programming in Lisp for quite a lot of time. I have some software written in Clojure. Who knows Clojure as a language? Clojure is something like Lisp, but in Java. So it's very popular for functional programmers because it compiles to Java, to bytecode. So I was writing in Clojure. But for me, thinking like functions is way more difficult than thinking like objects. Because our world is objects. So we are surrounded by objects, and it's easier for us to think about objects and say that there is something in front of me, and it has a name, and it has a price, and it has a title. Then there is a function which is nothing. And I mean, for me, it's difficult to think like functions. So I think object-oriented programming is more powerful, but very close to functional programming. Very, very close. Thanks for the questions. We're out of time. See you next time, Wednesday at 7, right? We start at 7 sharp. Okay, see you on Wednesday. Thank you.